Hello, thank you for joining us today. We are delighted to have two people from Regenesis that are going to be co-presenting for you today, Todd Harrington and Paul Erickson, and they're going to be talking about the performance of a new activated carbon amendment that can be used for petroleum hydrocarbons. Now, I know many of you on the webinar today are familiar with the products that Regenesis offers, and you've likely used them at your sites. And many of you are probably familiar with how Microbial Insights products are very complementary and can be used to help you monitor and understand the application of the great products that Regenesis offers. And we've been working with Regenesis very closely for more than 18 years. So I'm really delighted that you're here today and that they're going to share their experience, and we'll talk a little bit about the tools and how we can use them and a little bit about how we work together. So as a short introduction of our speakers today, we have Paul. Paul is the Senior Research Scientist with Regenesis, and he currently specializes in the research and development of new products. Dr. Erickson led the development of the Petrofix Design Assistant application, and he played a role in advancing Petrofix as a treatment technology. Todd Harrington is the Global Petrofix Product Manager, and he collaborates with sales, operations, and with research and development. Todd has over 20 years of experience in the environmental restoration industry, and he's been with Regenesis since 2004. And Todd and I have worked closely together on a lot of projects over these many years, so I'm delighted to have both Paul and Todd speaking for us today. Now, if you look at your GoToWebinar, I've attached two handouts that I think you might find to be very beneficial to you. You can download these for you to be able to use. The first is a Petrofix brochure, and it's going to give you an overview of this new technology, kind of a glance of what you're going to be looking at, how it works, the activated carbon component of it, and it will cover kind of a base primer of what they're going to cover in the webinar today. So that handout I think could be very useful for you in future access. And then the second handout that you're going to see is called MI Petrofix, and this is the analysis handout. And this is going to talk about some of the quantitative PCR assays that can be really useful for you. So we can use qPCR to accurately quantify different microorganisms, different biological pathways that are of interest. And this assay in particular, the QuantArray for Petroleum, really targets all of the known aerobic and anaerobic petroleum assays that we have available. So I would recommend at the end of the webinar that you take a quick look at this, and then feel free to contact either of our companies. Both of us are very customer service oriented, and so we would be happy to walk you through any questions that you have. So please note that this webinar is being recorded, and we're going to make it available on the resource section of the Microbial Insights website sometime this week. You're going to be getting an email link if you registered for the webinar today, and that way you'll know that that is now available for you to view. After the presentation, we're going to have a short question and answer session. So as Todd and Paul are speaking today, please feel free to go ahead and type your questions into your GoToWebinar panel. And at the end, we'll answer as many of those questions as possible. If there's questions we don't get to, then either Microbial Insights or Regenesis or a combination of us will work together to get those answers out to you. So without any further ado, I'm going to go ahead and turn it over to you, Todd, to get started.
All right, thank you very much, Dora. It's my honor to be here and pleasure to be here. You know, as you said, we've worked together off and on over the last 15 years, and I remember traveling across the US on seminars that we would do together, and it was always exciting to see the new technologies that you have. So certainly excited for everything you're going to bring to market here in the future. Today's talk is the performance of a new activated carbon amendment for bioremediating petroleum impacted sites. I do want to give some thanks again to Paul Erickson, who has spent probably the better part of a year you know, working on this and helping us commercialize this technology. So excited to be co-presenting with Paul today. As far as what we, one second here. My slide. There we go. All right, as far as the outline of what we hope to accomplish with you today is, I know many of you know us, but I think there's probably some new people on here who haven't worked with Regenesis, so I'll do a brief introduction to who we are. I'll get into describing what this new activated carbon product is and some of the special features about it. And then I'm going to transfer the talk over to Paul, who's going to talk about the bioremediation of petroleum hydrocarbons in conjunction with this new carbon product, including some of the beta tests and microbial results that we have today. So really just getting into who Regenesis is. Like, this is for people that maybe new to in situ, who maybe haven't worked with us in a while. Regenesis, we develop cutting edge technologies to clean up soil and groundwater in situ. And we do that by specializing in the research and development and commercialization and application of these technologies. One of the things that I've been most excited in my time here at Regenesis for the last 15 years is really the R&D side. It's always fun to go back in the lab and find out, kind of what we're doing and what we're working on. And, over the years, we're at our 25-year anniversary right now. This year, we released the first oxygen release injectable product 25 years ago called oxygen release compound. And so things have certainly grown since then to where we have over 20 products and iteration of products that we've been able to develop. And we use a lot of data that we collect in the field and the lab to develop these so that they have the longevity, the mobility, the reactivity that we want to have, with these solutions. But the real application comes in sector 2 of this this circle that we have there to show the 4 kind of areas that we focus on, and that's really implementation of these. And one of the exciting things is as we implement these, we're comprised of former consultants, geologists, engineers, scientists located across the US, in Europe, to assist our customers in this. And we get to rely on more than just one technology now. These technologies cover enhanced aerobic biodegradation, enhanced anaerobic biodegradation, in situ chemical oxidation, in situ chemical reduction, bioaugmentation, muscle mobilization, and the topic of today's talk, which is in situ sorption and biodegradation. So we'll get into that in a few minutes. And I'm not really talking about it, but as we've grown to service our customers, we also have a turnkey application division called Regenesis Remediation Services, which are not necessarily applicable to this technology today. That'll be, I'll go over that in detail a little bit later. And also a section that helps our clients with their VI mitigation needs with vapor membrane. All right. So as far as locations, the best way to reach us is through the regenesis.com website or petrofix.com website. We do have district managers and scientists and support staff located across the US and Europe that have regional experiences and insights into local regs and such as that, so that we can bring a high level of service to you for your site. All right, let's get into the meat of our talk, and let's talk about the activated carbon amendment overview. The trade name, the official name of this technology is called Petrofix Remediation Fluid. And the fluid properties are really important. I'm going to get into that here in the next couple bullet points. Let's talk about exactly what is Petrofix and what are we doing to try to treat petroleum hydrocarbon sites. Well, it is a product specifically formulated for hydrocarbons by using a dual remediation approach. The first thing that we do is that we use carbon sorption to pull contaminants out of groundwater and hold them in place and create that risk reduction and contaminant reductions in groundwater, and then followed by anaerobic, or the stimulation of anaerobic bioremediation. So this approach is going to treat the usual suspects such as BTEX, TPHG, TPHD, MTBE, naphthalene, etc. Really anything that is anaerobically or aerobically degradable and also has an affinity to absorb the carbon is going to be, highly applicable for this technology. As far as concentration ranges, because we're dealing with both bio and carbon, this technology is appropriate for any time you need to get to an MCL all the way up to relatively high concentrations, but not LNAPL treatment. So I want to make that clear that if you've got a site where you've got continuous observable free phase contamination, it's probably best to proceed or consider excavation in situ chemical oxidation, and or other mass removal, source removal technologies to then potentially transition into Petrofix. So another bullet point is it's a liquid delivery. It's a liquid product. Pardon me, I'm getting some splash pages here. Okay. The product is a liquid by intent of a very small carbon particle size, which I'll get into in a couple slides, that allows for low pressure, non-fractured placement of material in the aquifer and without impeding groundwater flow. Third point on that is that this is a self-designed, self-apply approach. The importance of this is because we don't normally do this. Anybody that's worked with Regenesis in the past is used to calling us up, calling their local district manager, supplying a set of data, and then we chug through that for you, and we come up with a remedial design approach for you in a week or two, typically. And that's worked well, for quality control and great results for the remediation projects we work on. One of the things I was looking at the EPA site today, there's still over 65,000 UST cleanups that haven't been done in the program, and there's a high interest in this technology, and a lot of these sites are relatively small, or they can be big, but we think that because of the nature of it, because of the concentration ranges that we can hit, it's well suited for an online approach where people complete their own designs and injections with support from us. Specifically, what's in the drum? What do we ship? Let's talk about that a little bit. So this 1 to 2 micrometer carbon comes as a liquid. I do get asked every once in a while, is it a powder? So we're not shipping a powdered carbon. We are shipping, it's already in liquid concentrate form with plus 30% by weight is shipped in 55-gallon poly drums. Within that poly drum, we do pre-blend calcium sulfate dihydrate as an electron acceptor within that drum. And in addition to that, we provide a shrink wrap to the top of each drum, a 20-pound bucket of your choice of an electron acceptor blend. The 2 electron acceptor blends are as follows. The first, and our preferred method, is roughly 50% ammonium sulfate and 50% sodium nitrate. It goes up and down a little bit within the 40 to 60% range showed here. We think that the combination of these 2 electron acceptors has the highest optimal effect because of syntropic processes that Paul is going to get into with his slides. If nitrate's of particular concern in your state or province or where you're at, then we also have a nitrate-free blend, and that is roughly 50-50 ammonium sulfate and potassium sulfate. So it arrives on site, as I said, already in a liquid. Usually people just pop the drum off, mix it up with a drill or a lightning mixer, and then once diluted, adds the electron acceptors in the white bucket to the mix. It's not that difficult to do. It uses routine mixing and injection equipment. Nothing super specialized is needed, and it is safe to use around infrastructure and just safe to use in the field. You just need modified level D to safely handle this in the field. So one of the things that I think would be helpful to think about is where would I apply this on a site? And what helps is that as a liquid, how could we apply a liquid to a hydrocarbon site? I think that's helpful. So the first option is tank removal and upgrades. So this has been a big part of the industry where people will pull out leaking underground storage tanks or formerly contaminated soils. There's always a little bit left behind. It's great to put an amendment down in the base of that as an insurance policy, and Petrofix would be easy to use, either by pouring directly into the wetted base, if there's already groundwater down there of an excavation, and mixing around with a track hoe, or even just diluting and spraying it in from the side, very easy to do. I've even had people suggest injecting in injection wells into the gravel backfill around existing tanks for cleaning up contamination. So entirely possible to do. The most common approach is a grid approach for tackling a source area, knocking down some of that submerged smear zone, etc. Very popular approach, saying using direct push. And then the third, I've been surprised that there's been more interest than I expected initially, is the use of Petrofix for a barrier application, say putting it along a roadway to prevent BTEX contamination from going off site. Can be very effective. So let's get into a little bit of how this works. I think this is important to understand the efficacy of this technology. The dual function starts this way. When we dilute and inject this product into the ground, typically with direct push, you can also use injection wells. The material, the 1 to 2 micrometer carbon in it, does absorb or attach to the soil particles. And so what we're seeing here is a scanning electron microscope image of a sand particle that has flakes on it, the rough surface. That rough surface is not part of the sand surface. It is actually the attachment of the 1 to 2 micrometer particles to that sand particle. And so once in place, you have a sorption surface on there. And I want to make a note that the openings between the sand particles remain open. So we're able to apply this and coat the soil without occluding or preventing flow through the aquifer. So as things flow through the aquifer, I have an animation here that shows benzene in the pore space, and it will attach to the Petrofix particles on the soil and then hold in place. They'll come out of solution, and at that point we can stimulate anaerobic degradation and cause destruction of contaminants. We are adding nitrate and sulfate, and the reason we do so is in large part because we want a soluble electron acceptor to flow with the product, so that as we inject it into the aquifer, and we are targeting, the more permeable zones, they are existing together. This cartoon that we're showing down here is a classic depiction of typical electron acceptor profiles in the subsurface or zones of different types of anaerobic bioremediation. The front of an aquifer, typically where you still have oxygen, being the most thermodynamically favorable, although providing oxygen in a soluble format is much more difficult to do. So using soluble forms of nitrate or sulfate are important to this. They're not as fast as, say, aerobic degradation, but they are effective in the long run. And what Paul will be getting into a little bit more later is that we're noticing too that the combination of adding additional electron acceptors supports a certain series of methanogens for syntropic remediation. So I'll let him get into the details on that. It's pretty exciting stuff. So those of you who work with us over the years are probably scratching their heads because you're thinking to yourself, well, doesn't Regenesis have a technology called plume stop? And don't they look alike? And you are absolutely right. They do look alike, and there are similarities. So I thought it worth putting in a slide to differentiate between this. So plume stop is another what we call a liquid activated carbon, primarily designed for large distal plumes, solvent contamination, as well as some low-level hydrocarbon contamination, but really Petrofix was designed for that. The two technologies are both 1 to 2 micrometer carbon. So both are intended to go into the subsurface using low pressure injection, non-fractured placement in an aquifer. So that gives you a nice even distribution. Where they start to differ is that plume stop typically ships before dilution at less than a 4% by mass concentrate, whereas Petrofix, we have a significant amount of more carbon at over 30%. It's intended to be a hammer at hydrocarbon sites, so a lot more sorption capacity. The other thing is that plume stop has a polymer coating, and that polymer coating changes the charge characteristics on the outside of the 1 to 2 micrometer carbon particle, and allows it to more sort of slipstream through the aquifer with farther ROIs to kind of keep it general on what it does. Whereas through the manufacturing process, we're not able to do that with Petrofix. So Petrofix injects as a liquid, it just doesn't have the same ROI. And so you are generally limited to about 5 to 6.5 foot on center for this injection. So that is a difference. We've already went over 0.4 and then 0.5. There is a bit of polymer biodemand. The coating that we use for plume stop does exert a bit of a biodegradation demand that can be wasteful for electron acceptors. It is actually a pretty minor load, but it is noticeable with changes in redox that you can see if you go into a pristine aquifer. The big difference is it's Petrofix is self-applied. I mentioned that earlier. It's a you design, you apply approach to where you can engage on the petrofix.com website and pull that together with you for you. But for plume stop, this is being used on PFAS compounds, solvent compounds, large distal sites where a lot of kind of work needs to go on that for the remedial conceptual model. And I would say that Petrofix on the mass that we're putting in the ground and the spacing we're on is a fairly forgiving technology. So let's get into a little bit of low pressure versus high pressure. What does that mean and why is that important? Why is that important to Petrofix in your site? I've got two pictures here. The upper left picture is a picture of granular activated carbon. And granular activated carbon is typically in the size range in diameter 400 to 1,000 microns in diameter. The second picture is a powdered activated carbon, and its particle size is usually in the 50 to 250 micron diameter range. What that means is these actually are larger than the typical pore throat size of most fine and medium sands and even silts. And so to overcome and get these materials in the ground does require the exertion of high pressures, which also usually results in the formation of fractures that are often about 1 centimeter or thinner in size across the site. With a 1 to 2 micrometer carbon going in as a liquid, we can lower the pressures quite a bit. We can emphasize high volumes. We are emphasizing trying to get into the more permeable parts of an aquifer. We're not trying to inject Petrofix into solid dense clay, but in terms of addressing permeable zones, coating an aquifer, preventing back diffusion, things of that nature, we can get into under pressure, low pressures, even silts at a site very effectively. So what that looks like, I've got a little animation here, is that an image of Petrofix on the left, which we would dilute, typically, 1 to 10 or more, typically to go into the ground, trying to coat at least 40% of the effective pore space of an aquifer, if not higher. And then say direct push being a typical injection approach. We do like to stress injection techniques where the tool itself allows for a larger area of injection so that you can inject over 1 or 2 feet at one time to stress sort of more of an even distribution in that zone under lower pressures of the Petrofix in the aquifer. And so when you do that effectively, it doesn't allow much room for contaminants to escape. And I think I may have already said it once in this talk, but I like to use the term spray painting. It's as if you're spray painting from floor to ceiling the entire permeable pore space of an aquifer. So it's kind of hard for benzene, TEX, other contaminants to make it out of that permeable zone and go down gradient. This is a core from an actual Petrofix site where you can see where we targeted. We got nice uniform distribution of this carbon. So I'm actually, this is the last slide that I'm going to have before I transition over to Paul, and then we'll certainly have more time for Q&A that comes up. But to engage with this, if you're interested, just petrofix.com is the place to go to sign up. Is a simple process. You do have an email that's sent to you that you need to click for you to set up your own account. But what's nice is that we've got a couple great training videos available to you to show you how to design and how to inject. If you know your site well, if you know the vertical injection interval, aerial extent, concentrations, and soil type, things of that nature, it's possible for you to get on here and engage, and within 15 or 20 minutes or less, have a design that you can print with output to send to a local driller for turnkey estimates. And certainly, and my contact information will be shown at the end. If you've got any questions along this route, please give me a call. But with that, we're gonna transfer over to Paul so he can get into some of the actual case studies that we have with Petrofix.
All right, thanks, Todd. And thank you, Dora, for the opportunity, for Todd and I to come today and speak a little bit about Petrofix, the work we've been doing. If you would advance to the next slide, please. So what I plan to do is talk through some of the science behind Petrofix, get into a little bit of the details that you see here in terms of how we see this as a remediation approach, and get into a little bit more details, as Todd mentioned, about syntrophic biodegradation, which is one of the themes that we're kind of wrapping this technology around. And after we walk through the science, we'll get into the case studies that Todd mentioned, were really the beta sites that we performed as a part of evaluating Petrofix. And then we will, as a part of that, we'll highlight the technologies, the products that Microbial Insights offers, and how we use those as really a good additional line of evidence that the technology that we're using, the treatment that we're doing, is it's behaving the way that we expect it to. So, as I mentioned, these are the three challenges that we see that Petrofix helps address in terms of a treatment. So I'll walk through each one of these one by one, but you can see them here and I'll introduce them. So the way we think about these petroleum contaminated sites is that there's three big roadblocks holding back remediation or rapid remediation. And the first one there is high concentrations of hydrocarbons, lack of terminal electron acceptors. As Todd mentioned, the sites are depleted of oxygen, nitrate, often iron, soluble iron and sulfate. And so they've gone methanogenic. We'll talk about how we can speed that up a little bit, how the treatment that we're doing helps to boost remediation efficiency. And then also this third point, this buildup of inhibitory intermediates. What does that mean? We'll get into the details a little bit on that. So next slide, please. So this one's, I'd say, rather straightforward, but a good reminder. So on a lot of these sites, there's so much petroleum hydrocarbons that are present in the aqueous phase that they become toxic to the microbes, even the microbes that metabolize them. So too much of a good thing for them, you might think. And so the way that we, I'd say, address this challenge is that, as Todd said, the hydrocarbons are adsorbed onto the activated carbon that's present in Petrofix, and that helps eliminate or greatly reduce the aqueous concentration. And we've got that benefit that they're still bioavailable. We have good evidence, which some of which we'll get into today, that even though these hydrocarbons have been pulled out of solution, they're still available to the microbes for biodegradation, and they use them as a carbon source. So that's how we address number one. Next slide, please. So the second one is, I think, something else we're all quite familiar with, and that's that these electron acceptors are used up quite quickly. So our petroleum for the microbes is serving as a carbon and an energy source. And so the second thing that they need then is an electron acceptor, somewhere to put those reducing units, those electrons. And so, like Todd said, the front of our plumes, the first thing to go typically is oxygen. So if you think of a redox ladder, if you're familiar with that, these electron acceptors are used up in the order that is more favorable for most of the microbes that are present. So oxygen, nitrate depletes quickly, then of course dissolved iron. And then your sulfate and methanogens, they kind of coexist in this strange area that we'll get into a little bit, that I'd say over the past 10 years we've learned a lot more about. But the way we address this, number two, this lack of terminal electron acceptors, is we provide some of those. And so, like Todd said, within Petrofix remediation fluid, there is a slow release electron source, the calcium sulfate. But then as a part of that, we add a nitrate sulfate blend. And the reason that we opt for this, and we would recommend customers use this when possible, is that there's evidence that it's beneficial. We see that on the sites that we've worked on already, And I've included here a citation to a great paper that they systematically looked at this. What's the benefits of using them together? And then there's also the simple fact that nitrate is better for benzene. So nitrate reducers are better capable of removing, nitrate reducers are better at eliminating benzene from these sites. And so we see that as well. So next slide. So the third point is, I would say there's been a lot of work in the past 10 years that's been eye-opening to people in this industry, and that's this idea of syntrophic biodegradation. And my point here is that by adding this nitrate sulfate blend, we think of it as almost a biostimulation step. And what we're kind of doing is kickstarting things that the effects of which will stay, will keep going after the electron acceptors that we add have been exhausted. And so typically on petroleum contaminated sites, the first microbes that are starting the removal, the biodegradation of our petroleum hydrocarbons here they're the fermenters. So the first step in the process is simple oxidations of our rings or our alkene chains. And as the fermenters work, they are breaking down these petroleum hydrocarbons into hydrogen, acetate, other low molecular weight acids. And then it's the buildup of these intermediates. If this occurs, then this first step becomes less and less thermodynamically favorable. So someone's got to get rid of those end products in order to keep the fermenters happy and working. And there's a diverse class of microbes that are able to do this, but methanogens being one of them, and sulfate reducers as well. So in the first step, when we add in our nitrate and sulfate, sulfate reducers, they prefer to use hydrogen and acetate and can respire onto sulfate when it's available. And I've included here another citation to a great paper that talks a lot, goes more in depth into this idea. And an excerpt out of this paper here saying that a lot of sulfate reducers, they're very metabolically versatile. So when there's sulfate around, they can respire onto that. And as it's depleted, they're able to partner up, I'd say, with methanogens who are then able to take those reducing units rather than giving it to sulfate. They can pass on that reduction and basically tie this whole process together to mineralize and remove, biodegrade our petroleum hydrocarbons. So the point being here that if you get the conditions right and you use a product like Petrofix where you get that absorption, the removal of your hydrocarbons from the groundwater, you may not need to add more electron acceptors after they're exhausted. So methanogens can finish the work. Next slide. And so we wrote a tech bulletin that gets a little bit more into detail in this. This is just kind of a plug for this here. And you can find it on the website. And there's some more citations to literature that explains this idea. And there's some good stuff in here. So if you get a chance, check this out. Next slide. So now we'll get into the beta testing. So as a part of the development of any new product, you've got to go out and once you've got the formulation right, take it to the field and see how this performs in the real world. And so with Petrofix, we were able to do that on 2 different sites. And you can see here in the picture on the right, there's Petrofix batch 1. So that's drum of the first run of this product that we were out in the field working with. And as Todd got into a little bit, this 5 to 7 foot injection point spacing is really important. So we opted to remove any transport polymer from Petrofix because, as Todd mentioned, it is an additional carbon source that has to then be degraded by the microbes. And so in some ways, while it's not much, it does add to the burden and get in the way of really what we're trying to do here, and that's biodegrade the petroleum hydrocarbons that are present on the site. So both of the sites that we worked on were relatively shallow, permeable aquifers, and this was just giving us a chance to pull out the different elements of working with this product that there are. So we knew distribution shouldn't be that much of a problem and really just focus on how this treatment works once in place. And as a part of the work that we did, we performed, as you might imagine, quarterly chemical, but then also microbial monitoring. So since we're offering this technology as a removal of groundwater contamination coupled with biodegradation of them, it was really important for us to follow the populations of the microbes, look at the functional genes that are present on these sites as they're being cleaned up. And so with that, let's go to the next slide. So like I said, we worked on 2 different sites. The first one was in Panama City Beach, Florida. And the site, you can see a map over here on the right, was a former gasoline service station. And there was a rather sizable fuel release back in 2007. And if you look at the picture, you can see there was an excavation area where they removed, I'd say, a lot of it, but I think they lost a lot of the residual mass. This is a relatively fast-moving aquifer. It's very sandy. And so that mass migrated underneath a road. And you can kind of get a sense from the picture on the left, but this whole area is just really completely covered with concrete. So there's a road and then sidewalk. So really there's not much access to the surface. So the stuff was sort of trapped under a bed of concrete. And you can see here the xylenes in 2016. This is the ISO concentration of xylenes. This is what we were cleaning up. They had done several different remediation or used several different technologies on this site with limited success. I think they tried some Fenton, a series of nutrient applications, but there were still these lingering low-level concentrations of hydrocarbons left. And so we were working around a relatively small area for this treatment and around a single well. So let's get it. Next slide, please. So you can see here, very fine homogeneous sand. This is really beach sand from top to bottom. We were working really right in front of the beach. We put Petrofix in on 10 direct push points and injected 1,700 pounds of it. And you can see here the concentrations, historical and really the ones that were present when we went into work. On the bottom here, you can see another nice picture of what this product looks like when it's injected into sand. So yes, this is sand. However, it was very fine sand. We did a particle size analysis on it, and it came back as 99% fine sand. So really no coarse sand at all present. And on this site, there's essentially no preferential flow. I mean, this is working in a sandbox, so it was a good opportunity to see how the product flows, really when it can go in any direction at once, if you will. Next slide. And so here's the performance data on it. So as you can see, these concentrations aren't overly high. And I would call this a moderately contaminated site, but you can also see that the performance has been quite well. So every sampling event since we did the application has come back non-detect. I like to point out that this site was also impacted by Hurricane Michael, and so that last December sampling point is after there was even a hurricane that came through. So the groundwater obviously came up quite a bit, and still the treatment seems to be effective. So we're still holding non-detects almost a year in now. Next slide, please. And so this is the microbial data that is really important as an additional line of evidence. With the next site, I'll get into a little bit more of the geochemical data that really helps us see, get a good picture of, a more complete picture of the biodegradation that's happening. But what we have here is, this is the data that we collect with quantum-array Petro with Microbial Insights. And the graph on the left, you can see along the x-axis we have time, and then y-axis is cells per mil. And so all these individual lines represent a different functional gene or microbe that we're getting by this qPCR method. So we're quantifying in the groundwater the DNA that's present and codes for particular genes that we know are capable of, so the genes that code for different enzymes that are associated with petroleum hydrocarbon biodegradation. And so the figure you see on the right comes off the Microbial website, and just gives you a sampling of some of the functional genes that we're following that you can find on the graph on the left. But really the point that I want to make with this slide is that we're following these functional genes, and you saw the data on the last slide. We've removed essentially all of the contamination from the groundwater, and yet the degraders are still there. They're still present, and they appear to still be capable of biodegrading the petroleum hydrocarbons that are present on the site. So that's really what we're trying to see is we want to see this biodegradation. We want to see microbial populations that are at least stable. And so, we're seeing exactly what we were hoping for with these data. I'll point out the top line is just total eubacteria. So we're staying in relatively high concentrations of degraders that we want to see. The next one there is the sulfate reducers. So there's a strong population of sulfate reducers on this site. Again, this is exactly what we want to see. These are the microbes that we're giving them electron acceptors, and they're able to work with the methanogens when the sulfate isn't there anymore to really eliminate or mineralize these petroleum hydrocarbons. And the next one down is PM1, which is an MTBE degrader, but it's also a rather indiscriminate degrader of petroleum hydrocarbons. Again, this site, I would say, started with a strong microbial population, and then even though we've taken all the contamination out of the groundwater, they're still accessing food. They're still able to do what they need to do to clean this site up. Next slide, please. Advance. There we go. All right, so for our final site here, we were in South Bend, Indiana, and this was a much larger, much more contaminated site that we were working on. So it was a part of a bulk petroleum fuel storage facility, and that you can see in the map on the right. This facility was down south relative to where we were working, and for years there was free product being recovered off of this site. So this, compared to our Panama City site, was a much more highly contaminated site. And before we get into the data, just remind you, we really were punching a hole in this site in terms of the contamination. Everything around it was contaminated. We weren't, as in the Panama City site, I'd say, intercepting contaminant flowing in, but rather really just punching a hole in a very contaminated site. And I think I forgot to mention the Florida one. They're going full scale, and as we get into this one, you'll see that this was a beta test as well as I'd say a pilot test, and this site they're also going to go full scale on it. But again, several other remediation strategies were tried before they tried Petrofix, and so let's go to the next slide and see what we did. Again, more heterogeneous soils, I guess, than the Florida site, and we injected a similar amount of Petrofix, even though the contaminants were present in much higher concentration. And you can see here on the graph on the right, the table, we were dealing with upwards of 50 ppm of dissolved phase, GRO and DRO. And as you can see, after the application, we really knocked these contaminants down quite a bit. They've come back a little bit since, and we really can attribute that to the fact that we worked in a small area that was a part of a much larger contaminated area. And it's interesting, you can see what's coming back in is what you would expect, the smaller dissolved phase, the benzene and the toluene, those are migrating into the area preferentially. But again, this site will go full scale application in May, and with that we should hopefully see the reductions for good that we would like to see on this site. So we were fortunate enough on this site to get better geochemical data. So if you go to the next slide, we'll start to get into that. And so when we inject our nitrate sulfate blend like we did on this site, we're going in at over 1,000 milligrams per liter of each. And you can see that by the first monitoring point, so we injected in May, and then the first point that you see there that's elevated in both nitrate and sulfate, this was in June. And what we see is that the nitrate is rapidly removed. So this being the better, more easily used electron acceptor by the microbes, we see the nitrate eliminated rapidly. And so this is one of those things that we tell people, if you can use the nitrate, you should. You don't, on these heavily petroleum contaminated sites, there's really no concern about it migrating off site if used as recommended. And so we see the nitrate reduced quite quickly, and then the sulfate following behind quite nicely. So this is exactly what we want to see. This is, again, good evidence that even though the contamination has been taken out of the groundwater, it's still, there's still biodegradation occurring. So if you go to the next slide, this is some of the more exciting data. So what we see here is this is methane in the groundwater. And, you know, all these sites, these petroleum sites, you know, they're producing methane already. So by using Petrofix, you're not causing any problems. Instead, you're helping to speed up this biodegradation process. And so what we see here is that after application, which is the orange dotted line, we see initially a dip in methane concentrations, but then we see an increase with time. And even though after our October sampling there, going into our February sampling, the electron acceptors that we added have been exhausted, and we're still seeing increased methane production, even though 90+% of the contamination has been removed from the groundwater. So it's adsorbed and yet still bioavailable and still being mineralized. So this is exactly the kind of behavior that we want to see. And again, this isn't any dangerous increases in methane, and we're not really doing anything different than the site already had present on it, but this is just great evidence that we're really mineralizing and treating this petroleum contaminated site. Next slide, please. So again, this is that quantum petro data that we're using as our third line of evidence here that we're seeing biodegradation. And once again, we see either stable or on this particular site, increasing concentrations of these functional genes in these cells that are responsible for biodegrading our petroleum here. So again, for whatever reason, the sulfate reducers are doing well, but then also PM1, we see strong degradation by them and growth. And you can see there's a couple of other functional genes that now that we've reduced the groundwater concentrations, it seems like we've seen a bit of a toxicity reduction, and these microbes are even thriving better than they were pre-application of Petrofix. So again, this is exactly the kind of behavior that we were hoping to see. Next slide, please. And so this is going a little bit further into what Microbial Insights offers. And this is what's known as a messenger RNA, mRNA analysis. So with the normal quantum petro, what you get is a qPCR method that's quantifying the just DNA copies that are present in your sample that code for particular genes that may be present that are, I guess, again, capable of biodegrading, or they code for genes that are making proteins that biodegrade these petroleum hydrocarbons. This takes it one step further and looks at who's really thriving, who's making, expressing these proteins, and I guess growing up more would be one way to put it. And so what you see is there's that aerobic MTBE. That's the PM1 that we see for whatever reason just thriving on this site, but also the Panama City site. This microbe in particular, you know, using Microbial Insights data, we're able to show that these microbes are not only surviving, they're thriving post-application of Petrofix. Next slide. So with that, I'll just sort of wrap up kind of for the both of us and point out that we hope that we've shown you some data here that convince you that Petrofix can be an effective treatment for petroleum hydrocarbons, really a total remediation package. And we walked through some of the microbial and geochemical data that support this treatment principle that we're standing behind. And really the idea is that if you're on a site where you know how much contamination is going to be is present and then fluxing out of your site, it's possible to design a treatment strategy that would require none or little maintenance after your applications. And so I've got this diagram here on the right showing that you might want to treat a former tank leak with a grid in the hot spot, and then perhaps set up a barrier to intercept the flow of contamination that might be migrating off-site. And so by doing this, if you can get the microbial population where it needs to be, you may not need to add any additional electron acceptors in order to get not only capture and removal from the groundwater, but full biodegradation of these contaminants before they head off-site. So with that, next slide. Just like to thank you for your attention, and again, thank Dora for this opportunity to talk to you all about the science behind this and introduce Petrofix. And Todd and I would be happy to take any questions you might have.
All right. Thank you so much, Paul, for that great presentation. And Todd, this was really intriguing, and we do have quite a few questions. So again, put your questions into the GoToWebinar software. We'll get through as many of them as we can in the next 10 minutes. Whatever we don't get to answer today, we will try to send out a little document kind of answering these questions for everyone. We'll get with Todd and Paul and get those answers for you. So the first question we have, Todd, is for you. Can this product be combined with other Regenesis products like ORC to help enhance your degradation as a whole?
Yeah, thanks, Dora. Appreciate that. That's a great question, and I actually meant to mention that early in the talk, but absolutely, even though we're stressing nitrate sulfate, one could, if so desire, pair this with oxygen release compound advanced, or even a mechanical, aeration system of some sort. There's nothing preventing aerobic degradation of contaminants absorbed to the Petrofix itself. So I guess the advantages there, if you do it, would be speed, of contaminant destruction, and so completely possible.
Okay, great. So Paul, this question's for you. Why do you feel that Petrofix is really useful for anaerobic biodegradation? Would it also be effective in shallow wells that are more oxygenated aquifers?
That's a great question, and I think that follows along really well with what Todd said. Absolutely. So if you get a chance and check out that first citation that I included, the paper, they talk about, in that paper they did nitrate and sulfate, but they really stress at the end of it in their conclusions that oxygen should be included in the mix when possible. So absolutely. The reason that we stress the anaerobic side of things is that it might be better for some sites to just set up the treatment, get it working anaerobically, really biostimulated, and then hopefully walk away. And our point is you don't necessarily need to add additional electron acceptors. But if you'd like to, or if it's a shallow well and it's naturally infiltrating, that's great too. That's just going to speed it up.
Great. All right, Todd, previously we talked about this technology and not using it as much in the LNAPL, but what about the smear zone where you've immobilized NAPL? Is the issue that you only want bulk floating petroleum, or can you use it in those smear zones as well?
Right. So yeah, I'd mention this, and you'll find that if you get onto the Petrofix design assistant, that there is a question, is LNAPL visibly present? We really use this as a qualitative flag to indicate that typically if it is present, in most situations, that's an indicator that you probably have significant soil contamination that could leach, be a continuing leaching source into that Petrofix zone. Now, Paul and I are really confident that this technology will handle tens of milligrams per liter in the dissolve phase, but there is an upper limit to where it could potentially be overwhelmed. And so we're not advocating that people inject this directly into LNAPL. We're acknowledging that. So I guess to answer the question, that's what we mean by that. And so it also doesn't mean that you can inject this into relatively heavily contaminated areas where there is some smear zone. You are going to get contaminants pulling out of the dissolve phase, you are going to get a destruction. Things will go into equilibrium. Things will partition off of this, transitioning from store phase contamination as it gets treated, ultimately resulting in contaminant destruction. But, that's more of a qualitative flag for treatment to help people out, if anything.
I think a good follow-up on that, Todd, is can you talk a little bit about the permeability of using Petrofix in different matrices, whether it's like a sand or a clay?
All right. So I did mention this, and so there is certainly at sites, we have contamination that has, that has sorbed into clay. We have contamination that is often, making it to what we call high K zones or high permeable zones, and often contamination that's coming out of those clays into those permeable zones in the process called back diffusion. So specifically as a liquid, we're targeting permeable zones. So these are going to have, some level of sand content in them. And so, if hypothetically, we're in a gumbo clay site in maybe New Orleans, and you're pressurizing hundreds and hundreds of psi, perhaps there's situations where we're not going to really be able to get Petrofix in where we want it to go. But I think most sites that have plumes that are migrating have zones. I mean, this has been my experience. I've been on sites injecting Petrofix or plume stop, or more specifically plume stop, where we have 3 or 4 different permeable zones on a single site over a 10 to 15 foot interval of various concentrations. And then we target those permeable zones to get the full coating. We're able to really stop migration and initiate and complete a lot of remediation there, so that we're achieving, preventing it from going where it needs to go and causing start remediation. So hopefully that helps. And Paul, I don't know if you want to add anything to that.
I think you pretty much covered it. I mean, really, again, the idea is we want to create a zone with the activated carbon that's somewhat of a speed bump for these contaminants and give it time to be biodegraded, let the natural processes take place. And as long as we can load the transmissive zones with enough activated carbon to meet the incoming flux and whatever back diffusion is occurring, and have biodegradation occurring on that what's coming in, that's the treatment approach that we advocate, even in tight soils, is find those transmissive zones, target those, and that's important in the designing your treatment. Is you want to look for those and know where they are ahead of time if possible.
Okay, so I kind of have a 2-part question for both of you here. So we've talked a lot about plume stop, which I think is a really interesting technology. And over the last couple of years, I've seen some great case studies and examples for how plume stop can be used at chlorinated sites. So maybe, Todd, could you start talking about the difference between Petrofix and plume stop and kind of clarify that for us? And then, Paul, could you end maybe talking a little bit about how we could use these in conjunction if we have commingled plumes?
That's a good question, and I think it's certainly going to be getting into this a little bit. So can they be used together? I would say yes and no, depending on the strategy. Certainly, if we're dealing with a hydrocarbon plume, typically we're using anaerobic conditions or using in situ chemical reduction that try to promote a certain process. And yes, with Petrofix, we're also trying to stay anaerobic, but I do see situations where they may or may not be mutually beneficial where they intersect. But certainly, I would say it's definitely a possibility. We just need to look at each site specifically and say, hey, does sulfate nitrate as an electron acceptor, from area A that might be impacting area B, negatively influence, say, of us using, say, a combination of enhanced reductive dechlorination with plume stop in area B. So if we can get through those questions, I certainly think there's going to be situations where we could probably use them together, and probably situations where we couldn't.
Yeah, to finish that off, I'd say just to briefly go into the details about ERD. When we're treating chlorinated ethenes in particular, we want the microbes to be using those as the electron acceptors. And so the idea is you don't want any electron acceptors present because that will slow down and interfere with this process. So it is, I'd say, possible to do a combined approach, but really if you're dealing with a chlorinated site, that's when you'd best be talking directly to Regenesis and let us help you come up with your site design. And if there's small portions of it that maybe you want to polish off with Petrofix for some reason or another, we can talk through that. But really for chlorinated sites, get in touch with us. And there's just a lot more that goes into those, and you need to be talking directly to us for those sites.
Now, I want to add, so Paul, that's a great answer. I also want to clarify that the way I partially saw this as well is that it may, as long as we're not impacting, say, an enhanced reductive dechlorination site with electron acceptors to prevent that. I mean, certainly it's possible to treat different areas of a site simultaneously, which I was also thinking about with these technologies, as long as they're not intersecting. So that's something that you probably want to talk with us about so we can evaluate that.
Okay, well, I know that we're pretty much out of time, but there are two questions that I feel that came in that are really important that I'd like to address, if everyone will bear with me for just a moment. First, can you guys talk a little bit about how the regulatory agencies feel about these products, kind of what acceptance and how the utilization has been?
Yeah, that's good. I think Paul and I should both kind of answer that. I can start off. Is that I've interacted directly with probably presentations, 3 to 5 states and staff. I have not had a lot of strong technical concerns. I think the use of a carbon is pretty straightforward. People understand that. It's relatively inert. And the use of nitrate and sulfate is at least as electron acceptors, and what they do in groundwater is pretty straightforward. So a lot of the questions have been more about distribution and delivery. How do we do this? And what we need to do. So that has been my experience. It's been generally positive.
I don't have a whole lot to add to that, except for, yes, I agree. And the little contact I've had with regulators, they understand what we're doing. And, we haven't yet had much pushback on the nitrate, because I think people really do understand that on these sites, when used as recommended, we showed some data that back this up. The nitrate just disappears so fast, and there's really no concerns. And that's about all I have to say about it.
Okay, great. And the last question I have is something that I'm personally interested in and that we've talked about a lot. Paul, maybe can you start this one, and then I'll add my 2 cents, if that's okay, about how we feel that we understand that there's some biological degradation that's going on with these products. You want to start on that, Paul?
Oh, sorry. Yeah, I was on mute. The challenge is really painting the picture. So that's been the challenge with Petrofix, but also Plume Stop is, people want to know how do I know that the contaminants are being degraded, because I can't see them anymore. And so really that's one of the benefits of partnering with Microbial Insights is, the best way to answer that is go and look at who's responsible for the biodegradation, and that's the bacteria. So if the functional genes that are responsible for these compounds being degraded, if they're still present, if the microbes that depend on these contaminants are still thriving, and then we have geochemical data that back that up. So really it's about using multiple lines of evidence to answer that question. So in this case, we have the quantum petro data that show us the microbes are still there, they're thriving in some cases, And then if we have the geochemical data that show the nitrates being depleted as we would expect first, followed by the sulfate. And then also we have other lines of evidence that mineralization is occurring, at even increased rates from what it was at baseline. So one piece of the puzzle at a time may not tell you the whole picture, but using them in conjunction, it's about really framing out the picture as best you can. And if you need even more evidence, that's when I'd say go to Microbial Insights and have them try stable isotope probing on your site to really prove to you that there's, the microbes that are capable of doing this are still there and thriving. They have other methods even that that can add on to that. Dora, you may want to add something else to that.
Yeah, actually, that's right on what I was thinking, is you really need the multiple lines of evidence to understand what's happening at your site. And to be honest, I had no doubt that this product was going to work. And I was really excited when Regenesis launched this, because we've been using activated carbon in our biotrap samplers for almost 20 years. And we see microbes colonize on the activated carbon. We see them use the sorbed compounds. Proof positive with stable isotope probing that they utilize the compounds and incorporate them into their biomass as they're growing. So we know definitively that things can be used from the activated carbon. I know there's particle size differences that we're talking about here, but when you get microorganisms that have a surface and a food source and all of these things fit well together, you're making kind of the perfect environment for bugs to utilize what's available, and Mother Nature's going to persist and things are going to thrive and grow. So I feel very confident in the data that we see from this technology that we are getting biodegradation that's happening. That mRNA data that you saw is proof that organisms are growing and thriving in this environment after this has been added. So obviously these compounds are still bioavailable to these microorganisms, or we would not see that phenomenon. They're not going to express genes if they're not active in utilizing it. So I think we've got a lot of evidence, and we're working with Regenesis to do more studies to kind of help evaluate this for you. But use the multiple lines of evidence. If you need convincing for regulatory agencies, we certainly have other tools like stable isotope probing or compound-specific isotope analysis, or simply looking at the expression of the microorganisms as that third line of evidence can be really valuable for you at the site. So these are products that I'm super excited about, and I'm glad to see them available in our industry. So that's my 2 cents in what I've seen over the last couple of years working with Regenesis on both of these. I know that we did not get to all your questions today, so we'll work with Regenesis. We'll put together a question and answer document that we'll send out to everyone that registered for the webinar. Thank you so much, Todd and Paul, for your time and for the excellent presentation and talking about this product. I'm delighted to see it expand from what we've been doing with chlorinateds over to the petroleum side. And thank you everyone for attending this webinar. Again, we'll have the recording of the webinar that'll be available on our website later this week. So if you can check on the resource section of the Microbial Insights website, it'll be there for you. And then you've got those 2 documents, the handouts that were available that you can download that'll give you some a little bit more information about this. And if you have additional questions that you come up with, feel free to email them either to Todd or Paul at Regenesis, or send them over to info@microbe.com, and we'll be happy to get with Regenesis and get the answers for you. So thank you again, everyone. Thank you, Paul. Thank you, Todd, for being here with us today.
Thank you very much.
Thank you, Dora.
Thank you.